In this part of our combustion lecture, we'll pick up where we left off, and we'll talk about where the energy of a combustion reaction actually comes from. Now, what we're going to talk about isn't actually just going to apply to combustion reaction, it applies to all reactions. So let's start with something simple, potential versus kinetic energy. Kinetic energy is energy associated with movement. If you've got a large bus driving down the road, the faster it goes, the more kinetic energy it has. If you have a smaller object driving at the same speed, it has less kinetic energy. So kinetic energy isn't just associated with movement, it's also associated with mass. Think about if you had a really big person running at you at 10 miles an hour versus a really small person running at you at 10 miles an hour. Which one would you fear more? So the mass actually plays a role in there. Potential energy is a little harder to describe because potential energy is energy of position or composition. Some things contain more potential energies than others simply because of what they're made of or where they're located. Imagine taking a rubber band and stretching it really far back and then letting go, snapping yourself in the leg, or even worse, snapping someone else. Imagine a bunch of explosives sitting there, undetonated, but still sitting there, like a stick of dynamite. Would you want to hold a stick of dynamite for a long period of time? Probably not, because you understand what it could do. It has the potential to explode. Chemical energy is a type of potential energy. Now, chemical energy is going to be the focus of the rest of our conversation here. Chemical energy is the energy that is contained within a bond holding two atoms together. If we look here, we've got a single bond, a double bond, and a triple bond. And they involve different atoms, but they also have something that's called bond order, single, double, triple. What that means is different number of electrons being shared. Now, the higher the bond order, the more energy associated with that bond. For instance, a double bond has more energy than a single bond, and a triple bond has more energy than a double bond. That bond energy has actually been determined for many different types of chemical bonds. We've got tables like this that exist in even the most simple textbooks now, where we see the type of bond, a carbon-hydrogen bond, a nitrogen-oxygen bond, and the amount of energy associated with it. If we look at carbon monoxide and carbon dioxide, we see that carbon monoxide has a bond. Carbon monoxide actually has a triple bond, but if we look just at the simplicity of it, it's one carbon-oxygen bond. Carbon dioxide has two carbon-oxygen bonds. If we ignore bond order for now, we can simply look at the fact that carbon monoxide has one bond, carbon dioxide has two separate carbon-oxygen bonds. Now, the truth of it is that carbon monoxide has one carbon-oxygen triple bond, which is not displayed on this diagram. Carbon dioxide has two carbon-oxygen double bonds. Now, those carbon-oxygen double bonds are weaker, but because there's two of them, carbon dioxide actually has a much higher total bond energy, something known as enthalpy. Now, enthalpy, when we look at the total enthalpy or the total heat of a reaction, is a way of describing how much energy is associated with that reaction. Here we've got our methane reaction again on the left. So we're combusting methane to produce CO2 and water. This is a really good diagram because we see carbon as a black dot, hydrogen as white dots, and oxygen as red dots. And what we can see is that in the progress of the reaction, we rearrange those dots. So what we can think of is that we're taking all the bonds and breaking them. We've got four carbon-hydrogen bonds. We're going to break all of those. We've got two oxygen-oxygen double bonds. We're going to break those. Then we're going to put everything back together in a different order. Think of a Lego castle like what we see here in the center. We take it apart all the way down to the individual little blocks, and we put it back together to build a Millennium Falcon. Now, when we're looking at an overall reaction, the question of is heat going to be released or is heat going to be taken in is answered by looking at the enthalpy or the energy associated with the bonds and the reactants and the products. And we get a we can do a diagram like this. This is called a reaction coordinate diagram, where we simply compare the energy on the y-axis to the progress of the reaction. Now, progress doesn't directly relate to time. It just means that the reaction is going from reactants to products. There's no specific amount of time indicated. On the left diagram, we see what's called an endothermic reaction. This means that energy is being taken in. We see a flat line at the bottom. This is where the reactants would be, and then the flat line to the top right, that's where the products would be. And what we see is that the products exist at a higher energy level than the reactants. The way we interpret that is that during the reaction, energy had to be put into the reaction. Another way of looking at it is that the bonds of the products contain more energy than the bonds of the reactants. This type of reaction would absorb heat. The diagram on the left are reactants that are at a higher energy level than the products. What we could say here is that the reactant bonds contain more energy than the bonds of the products. Now, once we form the products, that energy has to go somewhere. That energy will be released as heat, hence the name exothermic. So in an endothermic reaction, the products have higher energy. In an exothermic reaction, the reactants have higher energy. Now, how do we measure energy? Well, if we were in a physics class, we might look at the potential energy of an object, and it would be measured in joules. In common life, we measure energy in calories, and in chemistry, we do both. You can convert very easily between joules and calories. It's 4.18 joules per calorie. Now, calorie, that should sound familiar. If you look at a food label, such as what we've got here, we've got a pint of Ben & Jerry's ice cream. If we look at that value there, it says calories, 310. That doesn't sound like a lot. If we notice also that a serving size is a half cup, there are 4 servings per container, which means about 1,200 calories per container. Still not horrible. That's less than a day's worth of calories. But I want you to notice that that C in calories is capitalized. What that actually means is kilocalories, which means that's not 310 calories per serving. That's 310,000 calories per serving. And it's not 1,200 calories per container. It's 1.2 million calories per container. You might rethink eating the whole pint if it said 1.2 million calories per container on the top. Pizza is a common dish for college students, so let's look at that. If we look at pizza, one slice of pepperoni pizza we can compare. We get 250 calories from Little Caesars, 296 from Domino's, 330 from Papa John's, 370 from Pizza Hut. Now I want you to imagine that's 370,000 calories per slice, and there are 8 slices per pizza, which means if you eat the whole pizza, you're consuming almost 3 million calories. That's a lot. I think if that was published on the outside of the box, you probably wouldn't eat the whole thing. What that means, a calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. So if you eat the whole Pizza Hut pizza, that's about 3 million calories, which means you could raise 3 million grams of water by 1 degree Celsius, or 1 gram of water by 3 million degrees Celsius, or any combination in between. That's a lot of energy. Our body uses all of that energy in the same way that a combustion reaction does, except it's not in the exact same way, which is good for us. Here we've got a general reaction written for glucose in a combustion or in a cellular respiration situation. Combustion, we would take glucose and oxygen, add heat, and we would get CO2, water, and flames. Cellular respiration has the exact same reaction, except instead of heat, we use enzymes. Now, the overall reaction is the same, but the result is different. Why don't we burst into flames if this is really just a combustion reaction? Well, the science behind it is actually really complicated. We've got these compounds called enzymes, which are large protein complexes that help the reaction move more efficiently. To give you an idea of how much more efficiently, the engine in your car operates at somewhere between 20 and 50% efficiency, whereas your body operates somewhere around 90 to 95% efficiency with this reaction. The majority of the energy in that efficiency is not released as heat. It's stored away as other forms of chemical energy. So whereas in combustion you really just break the bonds apart and let all the energy go away as heat, in cellular respiration the same reaction takes place, but instead of just busting the bonds apart, you shuffle the bonds around to form new bonds. And in that way you're able to store energy away. What that means is that spontaneous combustion is very unlikely to happen. In fact, scientists have done the math. All the energy contained in the human body that is accessible as an energy source, for instance, glucose and protein, if it were all to combust at the same time, if it were to all to just not work the way it's supposed to, you still wouldn't catch on fire. Spontaneous combustion is a myth. Scientists have proven time and again that it's what people use as an excuse when they can't figure out the real reason for someone catching on fire. Now, cellular respiration, combustion, these reactions are both what are called oxidation reduction reactions, or redox for short. What's happening is that you have a transfer of electrons, and the difference between combustion and cellular respiration is the way that electron transfer happens. You have one molecule or atom transferring an electron to another. The molecule that loses electrons, or the atom that loses electrons, is the one being oxidized. Lose electrons, oxidized. The one that gains electrons is the one being reduced. Gain electrons, reduced. And an easy way to remember that is Leo-Ger, Leoger. Lose electrons, oxidized. Gain electrons, reduced. Another one is oil-rig, Oilrig. Oxidize is losing, reduction is gaining. Now this diagram has an extra bit of terminology on it. We've got a reducing agent and an oxidizing agent. The reducing agent is the one that's reducing something else. The reducing agent is the one being oxidized, though. The oxidizing agent is oxidizing something else. The oxidizing agent, however, is being reduced. When we look at combustion versus cellular respiration, I said that the difference is in how the electrons are being transferred. The reason why combustion is so energetic is because all the electrons are being transferred at once. The more reaction that's happening, the faster the thing goes. It speeds itself up. It's a chain reaction. Cellular respiration does not speed itself up. The electrons are being transferred two at a time. No matter how fast you transfer two, you're not going to make the next two transfer any faster. It's a timed, measured process. So the result of that is that in combustion you get a large amount of energy release all at once, whereas cellular respiration you get a very slow, measured energy release, which is why we do not burst into flames. Now, in the next part, we'll talk about oxidation reduction reactions and a few other types of reactions as well.